In this video, we'll talk about some of the theory of second-order linear equations and why they're so great as opposed to nonlinear equations. So for linear equations, they have some nice properties. They're always of a certain form, but it also means they're easier to solve and easier to analyze. So for a quick notational thing that we'll use going forward, I have a differential equation of the form like this: y double prime plus p of t y prime plus q of t y equals 0 equals anything. I'm going to define this left-hand side here as an operator, say L of y. So for instance, in this case, I would have L of y is y double prime plus p of ty prime plus q of ty. And the idea being whatever I put in here for y means I'm plugging into the equation. So basically L means do this stuff to any function I put in there. Do two derivatives, then add p times the first derivative, then add q of t times the function itself, and compute that, and that's what L of y is. So as a side example, if I define, say, L of y to be y double prime minus y as a simpler operator like this, I can then say that, say, L of sine of t is going to be, plug it in, take two derivatives, that gets me a negative sine of t, minus y itself is another copy of sine of t, so this is minus 2 sine of t. So basically this gives us a simpler way to write just the one side of the equation. This setup only works for linear. We don't really care too much about what that looks like for nonlinear, but for a linear equation, you can sometimes get away with seeing some nice results if you write this sort of operator notation for L of y, meaning take whatever function you plug in here and do this to it. Now, why do we like this? We like this because it was an easy way to think about certain results. For instance, for linear equations, we have this idea of superposition, which is that if I have two different solutions to a homogeneous equation, L of y being the left-hand side of the equation equaling 0, then the linear combination c1 plus c2y2 also satisfies the same thing. And this really comes down to a more fundamental property of linear equations, that they are linear in this operator sense, meaning that we have that L of c1y1 plus c2y2 actually equals c1L of y1 plus c2L of y2. So in essence, this L operator here is linear, and this is I can split it over pluses, and I can move constants out front. And this really comes from the same idea that the derivative itself is already a linear operation. We all know that for derivatives itself, if I look at AF plus BG and take a derivative, that is AF prime plus BG prime. So derivatives are also linear in this sense, and since we have a linear equation, it has the same property as well. So let's see why this statement here is true, and then we'll apply it to get the result that we have here. So this comes to plugging into the equation and simplifying things out. So what we have here is that L of c1y1 plus c2y2 basically means I want to plug this combined function here into my differential equation. So if I do that, this I can write out in the following way. So by plugging in c1y1 plus c2y2 wherever I see a y. Now, because derivatives are linear, like this argument up here, this will go inside to land on the y functions and leave the c's alone. So I can now put the derivatives through in that appropriate sense to get this. And now I want to group terms by the constant in front of them as well as the functions themselves, because c1's always paired with y1. So I can regroup terms to get something that looks like this, where I have c1 times a bunch of stuff involving y1, and then plus c2 times a bunch of stuff involving y2. But if we look back at what our definition of L was, this here is exactly L of y1, and this is exactly L of y2. So because the equation is linear, I get this sort of linearity result here as well, that this matches what we have here. And the only reason this works is because we had a linear equation in the sense that none of the y's were multiplied by each other or in weird powers. Otherwise, this sum and constants wouldn't have worked out in the appropriate way. But now what does that give us for this particular problem at hand? So we know that L of linear combination equals c1 L of y1 plus c2 L of y2. Great. But if we assume that L of y1 is 0 and L of y2 equals 0, then we get that for any constant c1 and c2, this is also 0. Which this is great because we have now, from two individual solutions, y1 and y2, built up an entire wide array of solutions for different choices of c1 and c2 that now have two constants that we're to determine. And since our initial value problems have two initial conditions for the function and its derivative, this means we might be in good shape for being able to satisfy initial conditions by picking appropriate values for c1 and c2. So that's why linearity is super useful in this case, because it means that I only need to find two individual solutions, and then I should hopefully be able to pick constants to meet whatever initial condition I want based on those two individual solutions. And going forward, we'll look at the ways where this works, ways when this doesn't, and how we can build up to finding solutions to initial value problems using whatever solutions we find initially to this linear equation.